Hi there. Today we are going to discuss vectors. We will start with a brief introduction. We will go over resultants and components, and then we are going to discuss two important vectors, force and position vectors. We will go over dot and cross products. Along the way, we will have example problems and provide you with some practice problems. Vectors are the quantity that are described by magnitude and the direction. So you need two information to describe the vector. Typically, vectors are expressed either as a bold letter, for example, capital V here, or sometimes when we are writing by hand, it's easier to put the variable V, for example, with an arrow on top. Examples of the vectors include velocity, heat flow, force, moment, relative position, electric field, and many more. We are going to focus on force, moment, and position vectors in today's discussion. So if you have two vectors, for example, A and a B vector, and if you want to add or subtract them, all you have to do is simply add or subtract their x, y, z component, or we call them as I, j, k component for Cartesian vector. So you can add x components, y components, and z components to get the resultant vector, or the addition or subtraction of two vectors. We can also write the vector in this form, where, for example, B vector is given by bx, by, bz, and we put those three components inside inclined brackets. Resultant of a vector, say, for example, if you have f1 and f2, the resultant vector is going to be vector addition of those two vectors, and it will give you the resultant. Or another way of saying that, fr, the resultant force, is a vector which has a components f1 and f2 along the directions 1 and 2. So we can add vector f1 and f2 to get the resultant vector. Or you can add f2 plus f1, you will get the resultant vector. When we are dealing with the Cartesian vectors, meaning x, when we are expressing the vectors in ij form or x and y component form, the vector can be expressed like this. The f vector, for example, has fxi and fyj, meaning fx and fy, they are x component and y component of the vector. Using the right triangle rule, we can express different information about the resultant vector. For example, the magnitude is going to be simply this length in the triangle, which is fx squared plus fy squared, whereas the x component is going to be f cos theta. Again, fy is going to be f sine theta, and the theta by itself can be defined using fy over fx, just using this triangle. So basically, we are solving the right triangle that we have here to get this information. If we have a multiple vectors or multiple vector forces, for example, in this case, we can use the vector knowledge that we just learned. We can add the x components and y components to get the resultant vector. Let's do one quick example. So as we can see, we have two forces acting here, the F1 vector and F2 vector. F1 vector 200 Newton is 45 degrees from y-axis. So if you want to look at the components of F1 along the x and y direction, they are going to be something like this. So one component along the x and one component along the y. One thing to note, the point of application of the force is not changing. It's applied at the same point. So x component is applied here, y component here at the same point where the actual force is applied, the resultant force is applied, right? So if we want to write the x and y component, so the near component cos 45 degree would be this. So Fy, the 200 Newton cos 45 would be this component, whereas 200 sine 45 would be this component. Now we can write these x and y component. We can start forming our resultant vectors. For the resultant vector, the x component will come from this, which is positive 200 sine 45. That would be one term. And the y component from y component is 200 cos 45. It's also positive. So this would be the FRY 200 cos 45. So far, we have only written terms from the F1. Now let's go over F2, the second vector that we have. So for the second vector, the x and y components are going to be like this. Again, point of application is still same. So these component forces are also applied at the same point where the actual force was applied. So the x and y component of this one is going to be 150 cos 30. The near component is cos 30. The further component is going to be sine 30. So 150 cos 30 and the farther component becomes 150 sine 30. So if we put them together, what we see, the x component is actually negative minus 150 cos 30. That's why we have it here. And 150 sine 30, that's a positive. So now we have included all possible forces, the components of all possible forces. We should be able to put them in calculator and get the resultant. So once we have the x and y component of the resultant force, we can find out the resultant force out of these two components. To do that, we will create a simple schematic. So 11.518 Newton acts along the x-axis and 216.42 Newton acts along the y-axis. So resultant would be something like this, Fr. And there would be angle that it will make with the x-axis, that's a theta. So now we can simply solve this right triangle and we will get the Fr, the length of this red line, and the angle theta. These are the two things that we need, magnitude and the direction. So magnitude, again, solving the triangle, since this side is going to be 216.42, this is 11.58, we can find out the hypotenuse from just taking the squares of these numbers and adding them together and then taking a square root. So we get 216.73. To get the direction, the angle theta, we can again write here, we can write the tan theta. Tan theta is going to be this side, the vertical side divided by the horizontal, which is 216.42 divided by 11.518. And if you take the inverse tangent through your calculator, we get it to be 86.95. So these are the two quantities that we were interested in, resultant and the direction. Let's go over another example where we try to find out x and y component, where vectors may be expressed in terms of the slopes. Instead of writing them as degrees, we can sometimes define the direction with the slope. So for example, in this particular case, we have four forces. Obviously, F3 and F4, they are acting in negative x direction and they do not have any y component. So we only have to worry about F1 and F2. So what it really means, the F1 force 8 kilonewton is acting along this line. The 3/5 of this component would act along the vertical direction. In this case, that would be negative y, right? And 4/5 will act like this. It will be the horizontal component. Same thing for F2. 3/5 component would act horizontally, whereas 4/5 component is going to act vertically at this point. So the horizontal component is 3/5 of the 6 kilonewton, which is 18/5. The vertical component will be 4/5 of the 6 Newton. And for the F1 force, it's again 32/5 in the horizontal and 24/5 in the vertical. So we have all x and y component for each forces. We can write them as a vector. And as you can see, if we add them together, although this question doesn't ask, but if add all the forces to get the resultant, all the vector forces, in fact, in this case, they all add up to 0. Let's move on to the 3D vector. For example, if you have an x component of the vector, y component, and z component, they physically represent a box where x component is one dimension, y component is one dimension, and z the other. And from the origin to the farthest point, if you draw a vector, that would be the resultant force. It's kind of a diagonal of that box that we have, right? So from origin all the way to the farthest point, that represents the resultant vector or the vector that we have for these three components. And that comes out to be fx square plus fy square plus fc square. There is another very important term to note for 3D vectors. We have a term called direction cosines. Direction cosines, essentially what it means is, if you have a resultant vector, how much angle does it make from the x-axis is going to be alpha. How much angle it makes from the y-axis is going to be beta. And same thing, how much angle that resultant force makes with the gamma is going to be the direction cosine in the z-axis, right? Alpha, beta, gamma. So these are three direction cosines. They give you the angle that resultant force makes from the x, y, z axes respectively. So the concept here is very simple. If you have the angle that force makes with the x-axis, the fx is going to be simply f cos alpha. If you know the angle that f makes with the y-axis, the component is going to be f cos beta, right? Fy. Same thing. Fz is going to be s cos gamma, because gamma is the angle that force makes from the z-axis. Another important identity that comes in handy when we are solving 3D problems is this cos square alpha plus cos square beta plus cos square gamma equals 1. What it essentially means, to define a force, if you are given the angle that force makes or the vector makes from two axes, third axis can be determined using this. So meaning if you know alpha and beta, you can find out gamma, or if you know beta and gamma, you will be able to find out the alpha. So this is very useful identity for when we solve 3D problems. When we have multiple forces acting on the system, then just like 2D system, we can follow and we can add the components in x, y, z direction to get the resultant vector. There is another vector that's really important for many engineering applications, that is position vectors. Position vectors, as the name suggests, it defines the position of a point from any reference point, in this case origin, right? So if you want to define a position vector from origin to that point where the coordinates are x, y, z, the vector is going to be x, I, y, z, j, k. So basically x, y, z coordinates. If you want to know the direction of that vector, just the direction, not the magnitude, what you can do, you can take the vector and divide it with the magnitude, the strength of the vector. So if you divide with the magnitude, all you will have is the direction, and we call that as a unit vector or unit direction vector. Unit vectors gives you the information about the direction. You can also define position vector between 2 points. For example, if you want to define from A to B position vector, that would be simply given by RAB, right? And that RAB would be simply XB minus XA plus would be the X component, YB minus YA would be the J component or Y component, and ZB minus ZA is going to be the K component or the Z component. So this would be the X, Y, Z component of the position vector. One thing to note, we are defining position vector from A to B. So we have to subtract the coordinates from B to A. So the starting to end point is A to B. So when we are writing the vector, we will subtract from B to A. And if you want to write the unit vector, the direction that point vector AB is pointing, if you just want to know the direction, we can divide this with the magnitude of the vector. That will give you the direction vector. Let's try to apply that to a problem. We want to express forces F1 and F2 as a 3D Cartesian vector. As you can see from the given information, it is very clear that we know the strength of the forces, 70 and 40, and we also know where they are pointing. We know their direction. But this direction information is given in terms of the coordinates, a more physical quantity. We need to express that in terms of the direction vectors to get the forces. So our goal would be, if you're able to find out the direction vectors along AC, and I know the strength, so we will have the force as a vector. Same thing, if strength is known 70, if I get the direction along AB, then we have the vector defined. So first step would be getting the coordinates. As you can imagine, for example, point A. So if you go with, say, for example, point A, so point A is located here. So to get to the point A in the X direction, how much you have to move? You have to move 2. In the Y direction, it's actually -3 because Y is positive this way. So you're going that way, so -3. And Z direction, you're going upward. So it's going to be a positive and +3. So the coordinates of point A is going to be 2, -3, and 3. Same thing, if you look at the point B, it's sitting right on the y-axis and it's 3 meters away along the y. And since it is on the y-axis, it has no distance from the x and no distance from the z. So we have 0, 3, 0. Same thing for point C. Point C is right here. And this point is again, it's a -2. It's going backward in the x direction. In the y direction, it is 3. And the z direction, it is 4 meters high. So now we have all the coordinates. Once we have the coordinates, we should be able to express our unit vectors. To get the forces, what we need is F1 is going to be 70, the strength, times UAB, and F2 is going to be 40 times the direction UAC. So this is how the vectors are going to be defined. So all we need is UAB and UAC, the two direction vectors. So UAB is going to be simply the position vectors from A to B. That's the direction where force is pointing, divided with its magnitude. To get the position vector, as we just discussed, what we have to do for A to B, we have to subtract coordinates of B minus A. So 0, -2, 3 minus 3, and 0, -3. If you do that, what we get? -2, 3 minus 3, 3 minus 3, 6, and -3. Now, this is just the position vector. We need to take care of the strength. To get the strength, if you, since you have the position vector, the strength can be simply, you can square the each terms and add them together. To get right the unit vector, all we need to do is divide each term with the 7. So now we have -2/7, 6/7, and -3/7. To get the UAC, we will follow the same. This is the position vector from A to C. Now, to get the strength or to get the magnitude, we will again square each of the terms. 16, 36 plus 1, add them together is 53. So now to write the position vector, we need to divide each term with 50, square root of 53. So these are the two position vectors. Now the problem is almost solved. So get the F1, to get the F1 vector, all we have to do is multiply 70 with UAB that we have, and for F2 multiply 40 with UAC. So if you multiply 70 times UAB, so each term needs to be multiplied with the 70, you get -20, 60, -30. And if you multiply each terms with 40, you get this as your F2 vector. You can further simplify them if you wanted, but these are the force vector in Cartesian form. Let's move on to the dot product. So dot product is a scalar product, meaning it is the final product you get as a number. And what it physically represents, it represents the projection of vector B onto A times the magnitude of the vector. So basically, dot product is used to find out the projection of the vector. So basically, if you do A dot B, basically you're finding out the projection of B over A, and then you're multiplying with the magnitude of A. So the way we compute this scalar product is simply we take the x component of each vector, two vectors that we're multiplying, and then multiply them together. The y components, multiply them together. Z components, multiply them together and add them together to get the total product. So simply x, y, z components, they get multiplied together and added to get the dot product. So dot product is also defined as AB cos theta, where is magnitude of A, magnitude of B multiplied with the cos theta. And cos theta is nothing but it is the angle between two vectors, A and B. So cos theta is the angle between A and B. Another point to note, scalar product or dot product is independent of order, meaning A dot B or B dot A, they are going to be exactly same. There is no difference whether which one goes first. All right. So it has some application. The application would be if you want to find out a component of any force, you can use the dot product. For example, if you're looking for a component or projection of any force vector along any direction, you can use this concept here and you will get F dot U. So if you take F, the force itself, and take a dot product with any direction you want, you will get the component of the force along that direction. One thing to note, if you get a negative, what it really means, the direction that you're trying to get the component, your component might be in the opposite direction. So typically you should get a positive if you have chosen the right direction. But if you get a negative number, what it indicates is your component is actually acting in the opposite direction that of a U. Let's try to apply that to the problem here. First, this problem has two parts. We need to find out the angle between F1 and F2. And then also we need to find out the F1 along AC. To find the angle between F1 and F2, we have to do the dot product. And what we can do is, we can do the dot product of two directions, then UAB and UAC. So we can write the direction UAB and UAC. And if I take the dot product, what we get UAB AC equals UAB magnitude, UAC magnitude cos theta. We know since these are the unit vector, these quantities are 1. So basically taking the dot product will give you the cosine theta. So in this case, since we have already determined UAB and UAC, the unit vectors, we can simply take the dot product of that to get the theta. And if you do the dot product, basically you multiply x components, y components, z components and add them together, you get 41 divided by 7 square root 53. And if you put that in calculator, you get 36.43 degrees. Now, the second part of the problem is finding the component of F1 along AC. To do that, what we have to do is we have to simply take the dot product. So since F1 is the force and we want to take that, we want to find the component of that vector along AC. So to get the component, we need to do the dot product. So F1 dot UAC will give you the component of force F1 along direction AC. Since we already have these vectors, F1 is already computed and UAC is already known, we can simply take a dot product and we will get the number as 56.32 Newton. So this would be the amount of force, the component of force that acts along the direction AC from force F1. So cross product is also called as the vector product. So if you have two vectors A and B and you want to take the cross product, so what you will do, you will again write your vectors in form of the determinant I, J, K, and AX, AY, AZ. These are the components of A. BX, BY, BZ is component of B. And once you open this determinant, you will be able to find out the final vector. It's a vector product, meaning you are going to get the result is going to be a vector quantity. And also, important point to note, A cross B and B cross A, they are not same. So if you switch the order, you get a negative number. And also the direction, in a way, the A and B is determined by the right-hand rule, meaning if you wanted to find out where this A cross B vector is going to act, it is going to act normal to the plane where A and B are acting. So again, the cross product is, again, physically what it means is if you have two vectors, if you take the cross, the resultant is where the cross product vector is going to act normal to the plane. It's going to act perpendicular to the plane of A and B. And one very common illustration of cross product is finding out the moment. Moment of a force, if you want to find a moment of a force, is R cross F. Moment is a physical quantity. It is R cross F. So meaning if you have a position where the force is acting, position vector which defines the location of the force, and if you cross it with the force vector, we are able to find out the moment. And in the cases where you have multiple forces, you can take the components, you can find the moment for each of the force and add them together. Let's apply the cross product to one quick example here. So we have, we want to find out the moment of 20 Newton force about point B. So point B is the point of reference here and force is acting at point A. To get that, what we need is MB, the moment is going to be R BA, or B to A. B is the starting point, A is the ending point. So that's what we need. From B, B wants to know where point A is. So it's from B to A, cross with the F. So if we define these two vectors and we can take the cross product of that, that will give us the moment. So to get the position vector, the first thing would be we need the coordinates. For example, the coordinates of point B, since it is only in the Z direction, 0, 0, 50. For the point A, it is 200 millimeter in the Y direction, and in the X direction, positive is this way, so it's a negative 10, so backward. And in the Z direction, it is still 50. So these are the coordinates, and once we know the coordinate, RBA is going to be coordinate of A minus coordinate of B. And that gives you minus 10 minus 0, 200 minus 0, and 50 minus 50. So this is our position vector BA. The next step would be getting the force vector, this force vector. As you can see, this force is 20 Newton. So there would be the 20 cos 60 component would act like this at the same point, right? And 20 sine 60 component would act like that. So we immediately see 20 sine 60 is acting along the positive x, whereas 20 cos 60 is acting along the negative y. And there is a no z component to this particular force. So if you write that as a vector, what we get the force vector is 20 sine 60 and the y component minus 20 cos 60 and 0, right? Now we can put these vectors in the relationship that we have for cross product. That will give you the cross product of these two vectors. So ijk, what we have here is minus 10, 20, 0. That's the r component, the vector. F is going to be 1732 minus 10, 0. And again, open it up. So for I, when you open, I times 200, 0 minus 10, 0. That's a 0. Minus j, and then you write minus 10 times 0, 1732.0 times 0. So it's also 0. But when we go with the k, then what we do, minus 10 is 100, minus 17.32 times 200. And that comes out to be 3,364. We have two practice problems for you. The first problem, we need to find out the resultant using these three forces. And the second question asks you to find out the moment, which is simply finding out the cross product of force with the reference point A that we have. I hope you found this useful. See you next time.